Welcome, D-Wolf Chemistry students. It's me, Mr. Cheney, with another brilliant tutorial. Today is one that's going to walk you through the lab that we did for ions and electroplating, which can be found in the online textbook through the Savvis app in Clever. So it's an interactivity from the textbook. So on Google Classroom, as we are looking at right here, you can see the assignment for that lab if you were not here for it in class. And it says after in-class Nearpod lecture, which if you were absent you need to do that Nearpod lecture as well. It was on ionic bonding. We will apply the principles taught in the e-text lab for electroplating. Electroplating is the process of plating a metal onto the other by hydrolysis, mostly to prevent corrosion of metal or for decorative purposes. The process uses an electric current to reduce dissolved metal cations to develop a lean, coherent metal coating on the electrode. So click the link below to access the lab. So you will click this and it will take you to the lab, and I'm going to go in through the lab right here, and let's just walk through the lab and see what we need to do. So here is the beginning and the preview. So ions and electroplating. An artist has created a special line of decorative iron spoons that she would like to protect from rusting by adding a zinc coating. She plans to use electroplating to add the zinc coating. Running an electric current from the iron spoon to the zinc plate causes the iron to become negatively charged and attracts positively charged zinc metal ions from the solution to its surface. The solution replaces its zinc ions from the zinc plate. For the electroplating to work, she needs to make a solution by combining water and a zinc salt. She needs a zinc salt that will fully dissolve in water. When it dissolves, the zinc salt will break apart into positive zinc ions and negative ions. This will allow electricity to flow and zinc ions to move through the solution. Help the artist choose the zinc salt that will work best for her project. So we're going to go to screen 2 here, and we're going to see the 3 salts that we're going to do some. So the directions tell us choose the ionic compound you would like to investigate. There's 3 types. We have zinc oxide, ZnO. We have zinc chloride, ZnCl2. We have zinc sulfide, ZnS. And so we'll choose the first one here, and it says you choose zinc oxide. Test and research zinc oxide, then investigate a new salt. So we're going to click test the salt in the lab, and what that's going to do is, this is our setup, and this is the salt solution. And basically what we're looking to see is if the bulb turns on or off, because if it's an ionic solution, if the salt is suitable for electroplating, it will be conductive, meaning that the ions broke apart in the salts, the positive parts of the ions and the negative parts of the ions separated, and they were throughout the mixture with the water molecules, and the light bulb would turn on. In this case, the unlit light bulb on the conductivity tester tells you that this water and salt mixture cannot conduct electricity, so record your observations in the data table. We'll click record data. Here's our table. Observations from conductivity test. Zinc oxide is the first one, and we can simply put that the light bulb remained unlit. So now the second part of this is going to the research. So observations from research, we'll go back to the lab, we'll research this salt, and we can see that for zinc oxide, ZnO, that when we put this into a water solution at time 0 minutes, 0 seconds, we have a solid crystal lattice, and at 5 minutes we have most of it still intact, but a couple ions have come off, a couple oxygens, a couple of the zinc ions, but not a lot. So they're not mixed throughout the solution, and that makes sense since our light bulb did not light up. So we're going to record that data too. So observing those 2 comparisons, and basically we can say something to the effect that the zinc oxide crystal dispersed or spread out very little throughout the H2O mixture. Which didn't allow it to be conductive. And so we'll do the same thing for all of the other salts, the other two salts. So once you've finished with that one, you investigate a new salt. You go to zinc chloride. You test the salt in the lab. This one, the light bulb's actually there, so you'll record your data. You'll research the salt. You'll look at the research for that. You'll make your observations in the data table for zinc chloride. And lastly, you'll do it for the third salt. So you'll test the salt, record the data, research the salt, record your data right there. So once you have all of those figured out, you're going to move on to screen 4. You have 2 questions to answer, and you're going to answer which salt dissolved the most completely, what did the salt look like after it dissolved. Second question, what relationship did you observe between conductivity and how easily the salt dissolved? These will be very obvious as you look at the results of your table, the light bulb versus the research screens. Slide 5, we have a prediction. We're going to make a prediction which salt can be used to electroplate the iron spoons, and you're going to use evidence to support your answer. That evidence would be within these answers and the data that you collected right here. Then we're moving on to 6, and this is where you can check your prediction. So you're going to select the salt that you predicted that could be used for electroplating. When you click on these, it's going to show you spoons side by side, and the salt that is the one that's successful for electroplating will show the zinc plating on an iron spoon rather than the other way around. Screen 7 gives us a question, what is your prediction? Was your prediction correct? Which salt made it possible to electroplate the spoon? And then describe the properties of the salt that made it useful for electroplating. And lastly, we have a question about those compounds. So the salts you tested were held together by ionic bonds. The compounds were made of 2 types of ions, positive and negative, that were attracted to each other because of their opposite charges. Some ionic bonds take more energy to break. Based on your investigation, which compounds have bonds that require the most energy to break? So this will be easy to answer based on the salt research that you did. So you'll answer that question, and then once you have all of those check marks complete right there, mine are not complete because I did not put my answers into the boxes, you will see a button right here that says turn in, and I will know to go grade your work. And that is the lab that we did in class on Tuesday, April 16th. I'll see you back in class.